Hey, have you ever had bruising after blood sample was drawn? I think I speak for everyone when I say it causes a lot of pain. When the coronavirus appeared and the number of infected people increased significantly, and patients had to install medical cannula from home and take intravenous injections, a problem appeared before, which is determining the vein, and the doctors faced many obstacles when determining the blood vessels of children, the elderly, and patients with dark skin, which may take a long time and may lead to severe pain and blood clotting in the patient. This made us think about using our project for an idea that helps doctors and reduce patients' pain, a device that can be used easily and is ready for use safely. Now, let's talk about the outlines of project. Firstly, intro, with presenting the main component and principle of work. Secondly, software, presenting the controller unit with programming and GUI. Finally, hardware, presenting design specifications, manufacturing process, and material selection. Development stages of Venn detectors. We looked at what was produced before and found that it was the first appearance of the Venoscope class and was based on transillumination rather than near-infrared, causing the result to be inaccurate. In 2006, the Venn viewer that uses near-infrared technology appeared in various forms. Screen and projector VD device, which works more efficiently than the previous type. We choose the screen VD because it's easier and the availability of components. We tried to make our project not just an idea, but could be used in hospitals and clinics. So our project was distinguished by being carried on a flexible device stand so that it's easy to move according to the patient's situation. Also, adjustable display, and we have implemented the graphical user interface so that it can be used easily. Now, we'll talk about the main idea of our project. It's based on near-infrared. It's close to visible light, present in the wavelengths range from 1 nanometer to 850 nanometer. Our device uses a near-infrared light source to capture invisible subcutaneous veins at a depth of up to 2 millimeter, and the near-infrared light is absorbed by hemoglobin present in the venous system in a different way compared to the surrounding flesh, and thus visualize the veins. How does a vein detector work? The local area of the upper limb is illuminated with IR beams, and then the rays have reflected on the camera. Then image processing takes place in the processor and improves the visibility of the veins. Then the enhanced image is displayed on a 7-inch touchscreen with graphical user interface.
Here you can see the electronic components of our project. Raspberry Pi 3 Model B, Raspberry Pi camera and IR LED module, 7-inch touchscreen. And these components we needed after the experimental operation: cooling fans and two power supplies. One is 5V 3A for the electronic components and the other is 5V 2A for the fans. Here we can see the device layout. The project consists of 3 base stations for transmitting data, which are the Raspberry Pi, the camera, and the screen. First, the Raspberry Pi sends a signal to the camera module to start shooting, and then the camera module drops the infrared light on the vein. Then the reflected waves bounce from it back to the camera, and then to the Raspberry Pi. Then they are sent to the screen to display after it's processed. For the selection of the processor unit, we have to make sure that the general specifications we need are available in it, which are sufficient processor speed to perform real-time image processing competitions, GPU to handle the captured frames, compatibility with camera and IR module. So after searching, we choose the Raspberry Pi to be our processor unit. The next step here is the operating system, which has been chosen after the experimental operation with different operating systems, and the Raspberry Pi OS 64-bit gives the best performance, so it had been our choice. Then we changed the configurations to be suitable for our project by expand the file system to use the whole memory card as a system file. And this image shows the usage of the memory and how much our system is light. We choose the GPU memory as 128 megabyte. We create an auto start file with GUI file to auto start on the desktop when the device runs.
This slide takes us to the programming software. We choose Python 3 to be our programming language, which is a high-level programming language. And we choose it because it's an easy language and provides all the libraries we need. Our main code is image processing, which based on two main libraries, NumPy for array and matrices, and OpenCV for applying different methods on images. Here you can see the image enhancement layer step by step, starting with the raw image, then change it to grayscale, then apply primary histogram equalization CLAHE method from OpenCV. After that, we do mathematical resampling as linear interpolation from NumPy, then apply secondary histogram equalization CLAHE method. The user interface. We had two options, the easy one and the complicated one, which is the command line interface, which needs the user to be aware of programming and needs a keyboard to enter the command. So we go to the graphical user interface, which is more simple and easy. This is the layout of our GUI, which contains a menu bar and standby image, which is a video stream takes its place. The menu bar contains two drop-off menu, which is the best type for saving space to have the full screen view. The main menu is on-off menu, which contains start and stop option to control the camera. The system menu contains the shutdown and restart of the system. We continue our working in programming using Python language. To create GUI, we use Detector library, which is a standard GUI library in Python, based on object-oriented programming to create each object in GUI. We also use Payload library to link between OpenCV and TK to show the video and label in GUI.
Hi, in the part of the hardware, we start with the design operational specifications, which is first, mounted on a flexible stand. Second, adjustable view angle. Third, easy assembly. Fourth, low weight. Fifth, efficient cooling. Now we go to the first specification, which is the flexible stand, where is the part that allows easy movement of the upper part of the device in all directions. The second specification is ease of assembly, and this makes it easy to assemble the device by anyone, even if he is not an expert in installation, where all what he needs is only screwdriver. Moving on to the third specification, we find adjustable view angle, where the adjustable part is installed in the screen holder, and with it, the screen can be located at a viewing angle equal to 0 with the x-axis, or it can be located at other times at a viewing angle equal to 0 with the y-axis, and the angle between those two angles can be controlled. This allows easy viewing to the nurse and ease of visibility. And now with the fourth specification, which is the low weight, where the weight is approximately 5 kilograms without the stand, and the total weight is approximately 15 kilograms, which allows the device to be easily carried and ported completely from a place to another. Now with the fifth specification, which is effective cooling, where the carrying part of the electronic devices is designed to contain two cooling fans, and they draw air from the outside and pass it on the surfaces of the electronic parts. and it's taken out from the side slots and passes to the rest of the lower parts through the lower slots shown. And this helps to cool the entire device to about 20 degrees Celsius to be in a safe thermal area. During the manufacturing process, the design has been made using SolidWorks CAD application and the manufacturing using 3D printing technology. Because of the high accuracy and high quality of the models produced by it, and it considered faster, more economical than other manufacturing technology, provides a printing of a complex parts with their details, as in our project, and it produces replica models in terms of texture and function. In material selection, the ABS material has been selected, which provides the following properties: excellent impact, chemical and abrasion resistance, easy thermoforming, and good dimensional stability. The mechanical properties of the ABS material is tensile stress is 45 gigapascal and the stiffness is 1.6 to 2.4 gigapascal. Elongation at break is 10 to 50%. Hardness short D is 100. Working temperature is 100 degrees Celsius. And finally, this is the final test of the developed vein detector device, where we can see the vein is very clear. And now, we'll let you with the demo of the project. Thank you.